My name is Nathan, here with Remy, and we did Project C, the heated rod with heat generation. So I started with just step one, drawing a simple diagram. What we did, we chose to do around 9 nodes just because it divided the total length evenly into like 15 millimeter sections. There's only one kind of new assumption that we made, and that was for K for the material of it. I kind of based it off what you said in that discussion post of we're using that like was like zircon or something. Found some data table online from Precision Ceramics USA. Said that that K value is around 3 watts per meter degree Kelvin, so I just used that as our K. For any of the actual like nodal equations, that only came into play whenever using the heat generation inside. So there's 2 different types of nodes that we focused on. One was for interior, and one was for exterior nodes exposed to convection. They're all pretty similar to the equations that we drive in class. The only difference was that there was heat generation. So I started out with the simple energy in minus energy out equals the change of energy. So Q1 minus Q2 plus the heat generation is equal to MC dt dt. So this is for our edge node with convection. So looking over here, we have Q1, which is convection, Q2 is conduction, and then we have a Q generation coming inside this node. So that equates to these equations right here. We got this 125 by taking the total watts across the entire rod, dividing it by the total area, and then multiplying by the nodal volume. And that was able to get us 125. Then from there, we just do some substitution, plug in values, and then from there, we're able to get this final answer right here. We got a BI and F naught. Those are just these constants right here just to make the computations easier in Excel. And then this is where K comes into effect for the heat generation inside. Did the same thing for the interior node. Same little derivation right there. And then here I was able to write out all the notifications for all 9 nodes. And then from there I was able to convert it into a matrix. And then from there I was able to plug it into this Excel right here. Get this matrix, invert it, and then multiply it by these C values right here, and then for it to cascade all across to give us this temperature distribution. We used a temperature of 300 seconds. Why? I don't know, seemed like a good number, and it didn't give us too long of an answer before steady state because we found steady state to be around 240 minutes.
In order to be able to visualize what was happening at each node, we have here color-coded and programmed on our spreadsheet. The red is going to be for hotter nodes, blue is going to be for colder nodes. That allows us to then go and pick certain columns that we wanted to analyze. So we started with 240 and then 0, and then I picked intervals of 50 seconds between to then have visually represented on a graph. So we started here at initial state. We moved to 50 minutes, 100 minutes, 150 minutes, 200 minutes, and then steady state. We then have an animation that we can show you of this actual trend. Let's go over there. No, one over. This is going to be the initial state, 50 minutes, 100 minutes, 150 minutes, 200 minutes, and steady state. Now you'll notice that the right side of the graph from node 5 to node 9 is generally going to be moving the most. The left side at T1 has been generally around the same area of above 22 degrees, but we see that this right side over here has gone all the way up to nearly 32, 33 degrees.
To add on to the Excel we did, just to make it easier, I added all of our givens on this column right here and use those to compute every single value in the matrix based on our nodal equations right here using F naught, BI, and any other constants that are needed. That allows us to quickly change, like let's say instead of 15 we have 10, it should quickly cascade throughout and give us new values. Also allows us to change different K values or anything like that and quickly do all the math involved. this is just a simple inversion of the matrix, and then multiplying that by this C array, we're able to get the next step in each of our thermal rod. Then use those values, give us new K, multiply that by the same inverted table, and that'll cascade down throughout. As for accuracy, the biggest thing we could do to improve that is add more nodes, as that wouldn't be too difficult to do just because, as you can see in this original matrix, it is pretty consistent throughout all the interior nodes. So it'll be very easy to expand from 9 to, let's say, 100 nodes. However, I don't really see that as too necessary, as I'm looking at this table right here. We have a pretty good distribution and a pretty good gradient going throughout. We also could do a smaller time interval, say around like 100 seconds rather than 300. But yeah, again, I didn't really see that as too necessary, as we do have a pretty smooth temperature distribution without having to have a super long file to capture all that data. Another thing that might impact our accuracy is our assumption for K, as I just picked the first number I saw, the first reputable source on the internet for a material that you implied that may seem right. But that could change a bunch depending on what the actual material we use is.